Hello, everyone. We are cosmologists who are at a cosmology conference, and we're here to answer your questions about cosmology. So before we get into that, I'll just briefly introduce what cosmology is. It's essentially the study of the properties of the universe when they're taken as a whole. So anything bigger than galaxy clusters, although even stuff that's smaller than galaxy clusters is often very relevant to cosmology. You need stars to measure the expansion rate of the universe and things like that. So today we'll be mixing between answering questions from a Reddit AMA that we did earlier in the day. Someone maybe could share a link to that in the description at the moment if they want, and answering your questions here live on HAPS as they come in. So what we'll start with is introducing each of us individually. So if we want to start with Ali Rida, do you want to introduce yourself?
Sure. First, my name is Ali. I'm a third-year PhD student at the University of Barcelona, and I'm working mostly in theoretical cosmology, which includes many different topics. And I'm very happy to be here tonight. Honestly, this is the first time I participate in such an event, so it will be a nice opportunity for me to engage with this new media activities. So thank you for that.
Thank you. Next, Angaran.
Hi, I'm Angaran. I'm a PhD student in theoretical physics, specializing in theoretical cosmology like Ali. I'm based at the University of Cambridge, and I am very enthusiastic about talking science with not just my collaborators, but also with the general public, whether they're willing or not so willing, I guess. Yeah, I'm looking forward to speaking to you guys about loads of cosmology today. And I'd also like to take this opportunity to talk about one of the organizations which I'm participating in called UniArc. I think Diana is just going to throw up a poster. So this organization is to help students from underrepresented and disadvantaged countries, and people from like persecuted minority groups, as this is something myself and various other members are passionate about. So we're massive diversity advocates in that respect. Thank you so much for giving me a chance to share that, and yeah, I hope you guys enjoy.
Awesome, thank you, Angaran. And Daniela, do you want to go next?
Hello, I am a postdoc at the Institute of Cosmology and Gravitation in Portsmouth, which is in the UK. Currently, I am working at looking whether the distribution of galaxies in the universe hints at the presence of more fundamental forces that we have seen so far. The fundamental forces that we know that exist are gravity, electromagnetism, and the forces that act on the atomic nucleus. Currently, I'm trying to see if there is more to that. And in the past, I've looked at whether the universe expands the same way in all directions, or whether there is any difference in this. And with this, that's it for now.
Thank you, Daniela. Ashley, do you want to go next?
Yeah, sure. Hi, so my name's Ashley. I'm a third-year PhD student at Newcastle University, and I actually started my PhD not focusing on cosmology, but focusing on quantum field theory techniques like the renormalization group and applying them to stochastic processes. But it turns out you can actually do that to help describe a period of inflation, which we might get onto later on. And particularly, I'm using that at the moment to try and describe the production of things called primordial black holes, which I would like to be able to talk about later. I'd also like to mention that I've been quite active in the UCU campaign here in the UK for increasing the rights of PhD students, and particularly trying to get them recognised as staff. So I'm happy to talk about that later.
Sorry to interrupt everybody, we're having a few audio issues, so I'm just going to restart the graphics server. We'll be back.
Do re-intros or not?
We're back on screen now.
Excellent, thanks. Next would be Alex.
Hi everyone, my name is Alex Goff. I'm a PhD. Hi everyone, my name is Alex Goff. I'm a PhD student at Newcastle University in the northeast of England. My research is focused on large-scale structures, so how the largest things in the universe form, and how we can better understand and model dark matter down to smaller scales. So that's what I work on, and I'm excited to get into answering people's questions today.
Thanks, Alex. Next is Rachel.
Hi, my name is Rachel Beaton. I'm a postdoc at Princeton University, and I think I might be the token observer on this panel. But I actually study the Hubble constant and measuring it using observations and measuring distances to stars.
Thank you. And finally, Katie.
Hello, I'm Katie Mack. I'm a cosmologist who studies dark matter and the early universe and how galaxies form, and occasionally I dabble in things like black holes and the end of the universe. I'm based at North Carolina State University. I'm an assistant professor, yeah, I'm excited to be here.
And I realized I didn't introduce myself. I'm Sean Hotchkiss. I'm at the University of Auckland. So we can start maybe with a question that I think Alex has volunteered to answer from Reddit. What are your thoughts on the ongoing attempts to modify Newtonian gravity to account for the observed discrepancies in galaxy motion instead of dark matter? Is there any viability to them? So Alex, start it, and if anyone else of the panelists want to speak, let me know.
Yeah, so I chose this one to start because I think it's something that seems to be, grab the public mind a lot, and the consensus amongst, I think, a lot of cosmologists, certainly not all, is that these modified Newtonian dynamic systems, are maybe interesting to study, but don't work nearly as well as the current system that we use, which is a combination of cold dark matter that doesn't collide with itself, and dark energy. So when dark matter was first discovered or first introduced as a model to explain galaxy rotation curves, it looked like, okay, well, maybe we can just modify gravity to do this and don't need to introduce new matter. But it's been a while since that's happened, and we have lots of other ways, systems that need dark matter to explain them. Otherwise, you have to come up with really convoluted systems to explain this. So we have lots of other evidence for dark matter, particularly from looking at the wiggles in the cosmic microwave background and how quickly structures form throughout the universe. It gets really difficult to solve these problems with just modifying gravity. So even if you modify gravity, most of the time to solve all of these problems, you also have to include dark matter. So it's not that modified gravity is completely ruled out. People still do work on this, but it's really difficult to completely do away with dark matter, which is, I think, what a lot of these modified gravity systems were originally introduced to do. But I think this is maybe a slightly controversial topic, so I'm happy to have other people, give their thoughts on this.
I think, Ali Rida, you have some thoughts. Do you want to?
Yeah, thank you. So modified gravity, when it comes to dark matter specifically, there have been a lot of debate about it. And I actually have been involved in a work related to that. In particular, there have been a few galaxies, I think 19, found with no trace of dark matter, very, very negligible trace of dark matter. And the argument was, if dark matter is supposed to be some new theory of gravity, then this effect of dark matter should be present everywhere because of gravity being a universal force. So the fact that these galaxies were found means that there's a big question mark on whether a new theory of gravity could be responsible for the effect of dark matter. And unless you want to tweak your model too much in order to fit the data, which then you would face what is called fine-tuning problems, it's highly unlikely, in my opinion, that dark matter is coming from a new theory of gravity.
Thank you, Ali Rida. So the next question that we'll have a go at answering was, what is the most likely expiration date for the universe? Katie, you haven't explicitly said you want to answer this, but I think I know you well enough that you will want to answer it. So I'm going to just put you on the screen.
Sure. Yeah. So I've recently published a book about the end of the universe and about different ways that could happen. It's called The End of Everything, Astrophysically Speaking. It's out in paperback. Yeah, so I've thought about this question. It depends on how we think the universe will end. So there are several possibilities for how the universe might end, but our best guess at the moment is something called the heat death, which is where the universe is currently expanding. It continues expanding. It's getting faster and faster in its expansion, and that leads to sort of everything becoming more isolated and colder, and everything kind of decays and gets dark, and the universe sort of fades away. And that takes a really long time. You can kind of come up with numbers for how long until the last black hole evaporates into the void and stuff like that. And they're ridiculously big numbers where you're putting, huge exponents on everything. And so, I mean, we can say, for example, that the smallest black holes that we know about, it'll take something like 10 to the power of 70 years for those to disappear. And that's just black holes that are about 5 times the mass of the sun. And we know there are supermassive black holes that are billions of times as massive as the sun, and those will take much, much longer. And, all the stars will be gone before then. And then, whether or not the proton decays is a whole other question. So what it means for the universe to really end, and how long that takes, you can get into extremely long time frames, and it kind of depends on where you put those marks in terms of the end. But I mean, there are a couple of sort of important markers of the end of the universe. For example, in about 100 billion years, which isn't that long cosmically speaking, we will be in a state where everything else is so far away from us that we won't be able to see other galaxies. They'll be moving so far. They'll be so far away, moving away so quickly. The universe will effectively be dark in 100 billion years. There will be maybe a few stars still burning in our own galaxy, and everything else will be so far away that we won't be able to see it. We won't be able to see evidence of the Big Bang anymore. We will lose that aspect of our cosmic history. And then it just gets darker and colder from there. So you can put sort of time markings around that, but generally speaking, we're talking about a really long time. And there are a couple of other possibilities for how the universe might end. Some of them could happen a little bit sooner in theory, but we don't expect that to occur. So in general, I think you can expect something interesting to be occurring in the universe for maybe up to 100 billion years, and after that, it's things get a lot sort of darker and colder and less interesting. So I don't know if that really answers the question, but we don't have a specific expiration date, and we can't say for certain which way it's going to go. But based on our current knowledge, it just kind of fades away for a really, really, really long time.
Excellent. Thank you, Katie. I think Angaran has some thoughts on this as well.
Yeah. Honestly, I just remember the question just being about the end of the universe. Could I just get a reminder of what the question was again?
The specific question was, what is the expiration date for the universe? But yeah, I guess to answer that, you need to know how the universe ends. So.
Yeah, exactly. So the expiration dates of the universe is a very interesting question, and there's actually been a theory by a recent Nobel laureate that many people might have heard of, called the Conformal cyclic cosmology. And this is an area of interest for me because what this theory is stating is that you could match the end of the universe, where we know everything. So as Katie put it so well, it's like you've got like black holes and stuff, and what actually happens with black holes, at least what we think from our theories, is that they emit radiation, eventually leading to photons. And we know that, from our experiments, that there is a period in the universe very early on, known as the cosmic microwave background, which kind of looks like this. And Penrose has this very interesting idea about mathematically mapping this early and late universe, and there are some other interesting theories actually done by some of my collaborators and supervisors back in Cambridge that actually says that although these two ends, or what we actually call boundaries in physics, are similar, they say that these are actually distinct. So unlike Penrose, they don't try to match them together, but they try to impose what does it mean to have two different boundaries. And this comes into a lot of interest when you start dealing with things like the wave function of the universe, which is one of the main topics of my PhD. And in the same way that when we solve equations in physics with different boundary conditions, the wave function of the universe will have to obey certain bounds because of these two different boundaries, what we call conformal boundaries in the early and late universe. So yeah, if people would like to know more about that, then I'll send some links into the comments on these kind of theories.
Cool, thanks, Angaran. I think we have a very interesting question next. So also, what exactly are quantum fluctuations? Are they responsible for the gathering of matter in one place and forming particles in celestial objects? And that's what decides where mass will be formed? Question mark. So I think Ashley has volunteered to answer that one.
Yeah, sure. So if we're talking about, quantum fluctuations seeding large-scale structure, which is what I'm assuming this is referring to, then these sort of quantum fluctuations can arise not just from the small uncertainty that you might be familiar with. You might have heard of something like the Heisenberg uncertainty principle, like this sort of inherent uncertainty when you measure the positional momentum of something. And this could be the uncertainty in something called the inflaton. So this could be a field which drives this accelerated expansion in the early universe, but also just quantum uncertainty in space-time itself. So we talk about quantum fluctuations in the metric, which is perhaps a lot harder to visualize, but it's basically just the fact that, we expect gravity itself to have some formal quantum description on some small scales. And what these fluctuations can do, and what inflation predicts, and it's like the main, one of the things it predicts very well, is what the spectrum of these perturbations are. And in fact, we can actually observe what these look like in the cosmic microwave background. And we see that the spectrum of them is roughly scale invariant. So this, shows that as we look over the sky, the sort of density perturbations that we see everywhere are sort of roughly equivalent. And so it is indeed fair to say that these quantum fluctuations will decide where you can have a slightly overdense region and a slightly underdense region. And it's going to be these overdense regions, which are then where you're going to form your large-scale structure. So, it's where you're going to form the first galaxies and things like this. So it's really quite a remarkable idea that, something that started very small, subatomic scales, inherent fluctuations perhaps of space-time itself have grown and become larger, and in fact are then the sort of seeds for everything that we see today, and in fact is the reason why we have things like galaxies and stars. Because if you didn't have these fluctuations, then the whole universe could have just been, for example, like homogeneous and everything like across every space. So there wouldn't have been any sort of initial seeds for collapse to happen and to create things like us.
Thank you, Ashley. So the next one, I think, it's quite a long question. So let me just read it out, and then I think Daniela has volunteered to answer it. How were particles formed, like protons and neutrons and electrons? What caused the imbalance between common particles and antiparticles? If particles and antiparticles explode when they come in contact, what caused the imbalance between common particles and antiparticles that allowed everything in the universe to be formed after the Big Bang? So Daniela, do you want to have a go at answering that?
Yeah, these are actually many questions and all very interesting, I should say. So how were the particles formed? So in the Big Bang theory, which was actually confirmed to a very high precision, in the very, very early times of the universe, everything was very different from the one we know it. The energy was very high, and there weren't yet the particles we know. But as it began cooling down, then the particles we know and love gradually started to form. In particular, one of the ways in which this happened is through the connection between matter and energy that was predicted by Einstein's theory of special relativity. According to this, mass is just one particular form of energy, so you can have stuff turning into light effectively, or light turning into matter. And from this materialization of energy into matter, in particular, you need to respect some specific rules that tell you how or how not you're allowed to do this. And you have to preserve things like the electric charge before and after, or other numbers that I will not tell you about that I have pretty funny names, but basically you have to go by the rules. Whenever you do this, you end up producing things like one proton, one antiproton. So for those who know what the antimatter is, you end up producing one matter particle, one antimatter particle, and so on. Now, the question is, what causes the imbalance between matter and antimatter? This is actually really interesting. I should start by saying that we don't yet have all the answers. We have some of the sources for this, but we know that we need more. This is referred to as CP violation, charge parity violation. And it's a set of physical phenomena that we know end up favoring matter. We have observed them in the accelerators, but we don't yet have enough of this to justify how in the end the universe was only made of matter. And the word of caution, if you end up meeting your antimatter alter ego, don't shake hands with them. You're both going to evaporate into lots of light. So just don't do that. What are these kind of physical phenomena? Essentially, they are phenomena associated with the decay of particles that end up preferring a universe to its mirror universe. So if you imagine what the physics may look like on the other side of the mirror, it turns out you actually have a physical way of telling whether you are on one side of the mirror or the opposite side. So imagine this experiment. You're in front of the mirror in the morning and your image in the mirror tells you, I am the real one, you are the mirror image. Well, it turns out you can actually make a physical experiment to know whether this is true or not. And some of these experiments show you that the process that favors matter is favored by physics. So there are some specific processes that end up preferring one process over its mirror image, where the mirror image would be the one producing more antimatter and the real image is the one producing more matter. So we definitely know that there are some physical processes that do this. The question is, we don't have enough of them. We have a hint of where they may happen. So for those who are familiar with it, it's called the strong CP problem. There is lots of research into that, but we don't yet have all the answers. Then the question was, the question was very long. So shall I perhaps continue later, just because there were lots of sub-questions to this question?
Yeah, that's a good idea. There was a question asked on HAPS as you were going. Why is antimatter not detectable or observable? Does someone want to have a go at answering that? Put your hand up on screen and I'll put you on the full screen. Okay, I'll do Ali Reader and then, yep.
So it's a very short answer. Actually, antimatter has been detected in several occasions, especially at CERN, where they have this large hadron collider where they are bombarding these protons and they're discovering so many exciting particles. And in fact, also at CERN, they are doing now optics experiments on anti-hydrogen, which is basically an atom formed of an antiproton and an anti-electron, which we call the positron. And they are studying its optical properties, which is something that I really find fascinating that we can do nowadays.
Awesome, thank you. I think I might just quickly jump in on that question. If I understood the motivation behind why is antimatter not detectable, it might have been meaning in the cosmological sense. And there the answer is that although Daniela was mentioning that in some subtle ways it might act differently, in terms of what we can observe cosmologically, it's exactly the same. So if there was a star made out of antimatter somewhere, going through fusion and emitting light, we wouldn't be able to tell the difference from here. We'd only be able to tell the difference if it met another star and it would interact differently. So we kind of can't detect it in that sense. I'm not sure if that is actually answering Stanley's question, but it was a go. So I might move on and answer a question partially myself now, which was about fuzzy dark matter. Let me just find where the actual question has disappeared to. Sorry about this. Ah, yes. What does fuzzy dark matter mean? Please tell me about fuzzy dark matter. Okay, so fuzzy dark matter is a term that has been used to describe a particular type of dark matter that is so very, very light that it actually acts a little bit like a wave. Anyone who has a background at all in quantum mechanics will know there's this thing called a de Broglie wavelength. And so an electron has a de Broglie wavelength that is very, very, very small, but can be detected if you have it going through certain diffraction gratings or things on a laboratory. But once you get very, very light, a de Broglie wavelength can become the size of light years or a tenth the size of a galaxy or something like that. And I don't have time to go into why light particles have large wavelengths, but it's true that they do. And then because of that, this dark matter has interesting properties in that it won't cluster inside these galaxies within this wavelength. You can't compress it much further. And that means that various things that would happen with normal dark matter or normal dark matter, but dark matter that isn't super light, won't happen with this fuzzy dark matter. It won't cluster as well, and therefore the centers of galaxies might not be quite as peaked if in the density as you go to the center. And there would also be potentially interference between the waves of this dark matter. You might get little globules of dark matter with an approximate size equal to the wavelength of these particles. I think Alex might also have some thoughts on this. So do you want to have a go, Alex?
Yeah, I do. So thanks for the... okay, yeah, I'm up now. Yeah, I do. So one comment I wanted to say about this, in addition to using fuzzy dark matter as a particular model of, maybe all dark matter is like this, and there are some particle physics reasons why we think this might be a reason, as well as cosmological, so that this solves some problems. But one of the other neat things about this is you can actually use the mathematics that's used in fuzzy dark matter in a certain way to model normal dark matter down to smaller scales, which is something that I actually work on a little bit in my PhD. So I just wanted to add that even if you aren't assuming that your dark matter is actually fuzzy, you can use some of the mathematics from that comes out of using fuzzy dark matter to pretend that your dark matter is fuzzy and solve some problems that way, which is just kind of a neat idea.
Cool, thank you. So we had an interesting question on HAPS a little while ago. So since the expanding universe is speeding up, is the rotation of the galaxies speeding up as well? I think Katie has volunteered to have a go at answering that.
Yeah, so when we observe the expansion of the universe, what we're seeing is that distant galaxies are getting farther apart from us and farther apart from each other, and that process is happening faster and faster. And we think that's driven by something we call dark energy, which just kind of stretches empty space and kind of pushes things out in some sense. But dark energy doesn't really do anything on galactic scales. So when there's a big concentration of matter and it's gravitationally bound, like in a galaxy, that's not affected by the overall expansion of the universe in the way that we currently understand it. And so galaxies will get farther apart from each other, but they'll keep doing their thing. Gravity has won over the expansion in those regions. So if you're in a galaxy, you're in a region of space where gravity is winning, the expansion is not. And so the expansion is not affecting how things move around within that gravitationally bound region of space. So so the accelerated expansion of the universe is really only something that we observe on the very largest scales, and it does have an effect on, you know, the growth of structure, how galaxies and clusters of galaxies formed over very long periods of time in the earlier, you know, as they were building up throughout the cosmos. But they're not. It's not making things. Is not changing the dynamics of the galaxy as it is in a way that we would be able to observe.
Awesome, thank you. Okay, Rachel, you've been very patient. Let's go to you. So I think this question is a very, very technical one. So you might need to actually unpack the question before you give the answer. But suppose there are two progenitor pathways for type 1As. Maybe some are single degenerate and maybe some are double degenerate. And maybe even some mechanism makes the occasional isolated white dwarf explode on its own. I don't understand the normalizations or corrections used for 1A distance measurements too well, but could multiple progenitors be a source of cosmological bias if the normalizations are imperfect for one of these populations? So yeah, maybe please unpack what a 1A is and a progenitor and things, and then have a go at answering the question.
Yeah, so supernova type 1A are really one of our strongest tools, one of our best tools in mapping the expansion history of the universe and the nearby universe. And supernova 1A are these massive explosions where we think a white dwarf, which is this end stage stellar product, explodes. The interesting thing about supernova as tools versus what physically is happening in a supernova is that in observations, we don't actually have to know exactly how the supernova work to be able to use them as tools. So when we talk about progenitor models for the supernovae, we're talking about what actually makes that white dwarf explode. So we have two scenarios that are the dominant scenarios. One is that you have one white dwarf with a friend star that it's orbiting. So a binary star where you have a white dwarf and a bigger star. And at some point, that bigger star can actually transfer mass to the white dwarf, causing it to go above the Chandrasekhar limit. So I don't know how to explain that concisely. But let's just say it can't get much bigger than 1.4 stellar masses. And once it gets bigger than 1.4 stellar masses, it explodes. So that's the single degenerate scenario. So you have a otherwise normal star and a white dwarf. The double degenerate scenario is you have two white dwarfs that are rotating around each other, and they eventually smash into each other somehow, and that causes the explosion. So those are the progenitor scenarios. It's very hard to have a single white dwarf all by itself explode. It's pretty much just gonna chill for the rest of time and just cool down for the rest of the universe. But if it can explode. Now, the thing is, what we use supernova to be tool is actually a product in the supernova experiment. So it's actually the radioactive decay of nickel 56. All that really matters to us is that we're seeing the decay of nickel 56. And what we do is we think the shapes of the light curve are self-similar, and so they scale up and down. And they scale up and down by the total mass of nickel 56. So when we standardize the curves, we're just correcting them all to a single mass of nickel 56, and then we use them as standardized candles. And that's the basic underpinning of supernova 1A. So hopefully I answered that question. And the more nuanced way to go into it is that we don't care so much if we have a mix of progenitor sources, as long as we can standardize them. But it does matter when we go to calibrate the supernova 1A, that our calibration sample matches the sample that we use for cosmology. And that's where things get a little uncertain because we can't actually tell the difference between these two scenarios right now. And so that's why people like me who measure distances to supernova 1A really, really, really want to sample as many supernova 1A as possible to make sure that we're averaging over some of these physical differences that might be an issue, but at least for right now, we don't think it's an issue.
Awesome. Wonderful. Thanks. Okay, Angaran, no pressure, but if you had to bet, what do you think was going on with the universe before the Big Bang?
I'm literally the worst person to ask this question to because I change my mind like every 5 minutes. So,
So don't speak for more than 5 minutes then.
okay, yeah. So, right, there are so many interesting theories. The currently like widely accepted theory, as like we mentioned quite a lot so far, is in inflation, which states in most of the models of inflation that the universe starts from a vacuum. So this vacuum, however you want to think about it, space-time was there. We're not really sure. I guess, like, yeah, explain why space-time was there is another philosophical question. But from that, you had particle creation coming from a rapid expansion in the same way that you have an expanding universe today. So I'm going to try and kill two birds with one stone here. Somebody asked whether you can match the inflationary region in the early universe to the dark energy dominated universe in the late universe. Yes, they are very similar, and it's interesting. And this is where actually the theory that I mentioned before regarding the future conformal boundary tries to not necessarily match the two as two equal kind of regions in the same way Penrose's conformal cyclic cosmology does, but says that they are unique but similar in certain aspects. And there's actually an interesting thing that people probably won't know is that the space-times that describe these phases, the inflationary and dark energy phase, are the same. Now, other alternatives are what we call, I guess, more cyclical cosmologies, such as bouncing cosmologies, and they're really interesting because they kind of seem a bit more natural because the cyclical cosmologies don't actually, in a sense, require a start for the universe, because we're basically saying the universe is sort of recycling itself over and over. But there are specific issues that we come across in the same way that we have a Big Bang singularity in the classical models, which still need to be resolved, to be honest. That we have a much more difficult issue of having a singular bounce, and that's a bit more difficult to navigate around. And yeah, these are like two very kind of different theories. But interestingly enough, and it's something came up. This is something that came up during the conference. Actually, is that what we call UV complete theories or quantum gravity theories, such as string theory, that they actually have solutions which show a duality between bouncing and inflationary cosmologies. So they might potentially be the same. And recent research has been showing that in the quantum gravity regime, this de Sitter space-time that I talked about are actually unstable. They can't be actually physical things that exist if we are to prescribe to certain quantum gravity theories. So yeah, there's a lot of ideas that I kind of threw at you, but the kind of main takeaway point is we don't know, but there's loads of interesting theories, and it just needs to be like developed a bit more. And one thing that could really help is the quantum theory of gravity. So yeah, I guess myself and others will keep bashing our heads against the wall until maybe some of us make a breakthrough.
Awesome, thank you. Okay, the next one I think is partially Rachel, partially Katie, but maybe we'll start with Katie because she hasn't answered a question for a while. I have vague recollections that expansion of universe pulls distant objects out of the observable universe. If so, then both size and mass of observable universe changes over time. Do calculations of likelihood of unlikely events, such as vacuum decay, take into account that the precipitating event has to occur within the observable universe in order to reach us?
Okay. Right. So I don't know if you've talked about vacuum decay yet on this stream, but the idea behind vacuum decay is it's a really cool idea where there could be an event somewhere in space, a sort of quantum tunneling event that would affect the Higgs field, which is this sort of energy field that pervades all of space. And it would create a little bubble of a different kind of space called a true vacuum. And that bubble would expand outward at about the speed of light and just destroy everything in its path. And if you think about the fact that the universe is expanding and that there are parts of the universe that are far enough away from us, that they're moving away from us faster than the speed of light. They're not actually moving through space faster than the speed of light, so it's all good, but there's more space happening in between us in a way that makes that part of space farther from us faster than the speed of light. You could imagine, like, maybe it's okay, this bubble could happen somewhere in that distant region and it'll never reach us and we're all good, right? And I thought about that when I was thinking a lot about vacuum decay recently, and it turns out that is possible. You could have that vacuum decay bubble happen somewhere else, but because it's just as likely to happen anywhere else in space, it's also likely, if it's happening way over there, it's also going to happen most likely somewhere nearby. And you can work out, like, if vacuum decay is going to happen, and it would probably take a really, really long time. It would be very, very far in the distant future. Do not worry about vacuum decay. Don't have anxiety about this. But if it were going to happen, you can work out that although it will never sort of destroy all parts of space, anyone in space will probably eventually run into one of these bubbles because they're going to be forming all over. So you can't escape vacuum decay just by living in a universe that is expanding faster and faster, unfortunately. But some part of space will probably continue expanding even in a universe where vacuum decay is happening kind of all over the place.
Awesome, thank you. Okay, the next one for Daniela will be, if we succeed in collecting more and better data on gravitational waves, what will that tell us? Are there fundamental questions we hope that data will help us answer?
Wow. If we really could get an arbitrary amount of information from the gravitational wave, well, it's basically Christmas come earlier. There's lots we could answer. One analogy that is made about this is that it's like before gravitational wave astronomy, it's like we only had silent movies. And with the era of gravitational wave astronomy, in addition to being able to observe light, we can also observe gravity waves. And so we have an entire new world to explore. So just to give you some example, what we could get from gravitational waves is a much better understanding of black holes, a much better understanding of neutron stars, but also if really we could have all the sensitivity we want, or the best possible detectors, basically, if I could have a dream detector at disposal, we could also learn about the very early moments of the universe. The physics we can get from some of the gravitational waves could let us explore energies that are completely inaccessible to particle accelerators on Earth. So, for instance, right now, the biggest and best accelerator that we have is at CERN. It's called the Large Hadron Collider, and it was mentioned earlier. But if we really could observe arbitrarily faint gravitational waves, then we could go many, many, many orders of magnitudes in the energy higher than that. We could learn about string theory, if string theory is the right theory of gravity at the tiny, tiny, tiny scales. And then this would also mean that we can learn about space-time. So basically, there is no limit in principle to what we can learn, because what gravitational wave astronomy has really given us is an entirely new window on the universe. And if you learn to ask the right questions, then you can always find a way to answer them whenever you open a new window. Actually, I will say something more about this. The point is, the moment you have a new window into a phenomenon, then in some sense, it's up to you to find out how you can use it to answer the questions that you have. This is a lot of work, but it's also a lot of fun.
Thank you, Daniela. Okay, so we've had a patient person from the HAPS live stream waiting for a while. Dark energy is a fascinating concept. How is that different from antimatter? Does anyone of our panelists want to answer that? Put your hand up and I'll put you on screen. Katie, okay.
Okay, yeah, so dark energy is at the moment mostly a mystery in the sense that we don't know what it's made of. But the way it acts is that it makes space expand faster. That seems to be all it does. It's just it's uniform everywhere in space. It's just expanding space. It doesn't seem to do anything else that we can see. Antimatter, on the other hand, is it's particles. It's things that we can detect in laboratories. We can see how these particles are connecting, or interacting with other particles. We can create antimatter in the laboratory. So it's also, its origins are mysterious in the sense that we don't know at the moment, and this was discussed earlier, why there's more matter than antimatter, and there are some mysteries involved in antimatter, but it's not really as weird as people think of it generally, because it is something that we work with all the time. I mean, even some of our technologies, like medical imaging, sometimes makes use of positrons, which is a kind of antimatter. So antimatter is a fairly normal stuff. It's just a stuff that has certain kinds of interactions with regular matter. Dark energy is very, very mysterious. It might be a kind of a scalar field, which is a sort of energy field similar to the Higgs field, which is this energy field that's throughout all of space and has something to do with the constants of nature and how particles work. It could be something like that, that has some properties, some dynamics, or it could just be a property of space, that dark energy is just a cosmological constant. It's something to do with how space naturally evolves. It's a term in the equations of gravity, and all it does is stretch space, and it doesn't do anything else, and it only acts on space itself. So they're both things that come up a lot when people talk about mysteries and science fiction and stuff, but they have very different roles in the universe.
Awesome. Thanks, Katie. Okay. I think I really like this next question because it's the sort of thing that it just seems intuitively obvious. And yes, it is something we consider. And yes, there are answers. So Ashley, what rules out dark matter being small black holes with no gas whatsoever around them, or just rogue planets or asteroids?
Yeah, thanks. Yeah, and I think you're right. It's something when one first hears about dark matter, you're just like, oh, so this is something which we know interacts gravitationally, but doesn't emit light or something. Hang on, that sounds exactly like black holes. So why isn't it just a bunch of them? And it's a good question. And the answer is that we have been thinking about it. And we sort of classify in general what could be dark matter into two categories. So there's things called WIMPs, which stand for weakly interacting massive particles, and MACHOs, which stands for massive astrophysical compact halo objects. And these are just sort of silly acronyms for basically either dark matter is some sort of particle we haven't discovered yet, or it's something quite large and dense like a black hole or perhaps a neutron star. And we can actually put constraints on the abundance of MACHOs, so black holes or neutron stars or things like that, through various different techniques. One sort of well-used one is something called microlensing. So if light goes near one of these really dense objects, it's going to be sort of deflected in quite a predictable way. And people have been looking in the sky for a long time trying to observe one of these sort of microlensing events. And as far as I'm aware, no one's spotted any. So in some certain mass ranges, we've been able to put constraints using things like this on the abundance of black holes and neutron stars, which put them below the abundance of dark matter. And there's also been some constraints from effects like Hawking evaporation. But as things stand, there is a mass window where all of dark matter could be made up of of black holes. And this would be around sort of asteroid mass. So as things stand, for all we know, dark matter could indeed be made up of black holes, which are about the size of asteroids. The problem with that, though, is that to form a black hole that small, you can't be formed due to stellar collapse. So there's this thing called I'm sure I'm going to pronounce this wrong, but the Chandrasekhar Limit, which basically tells us that you can't form a black hole due to the collapse of a star less than about 1 solar mass. It's a little high, but it's roughly that. And asteroids are obviously smaller than the sun. So you have to invoke some other sort of formation mechanism. And there's also a problem that you actually expect dark matter to be around before you get things like stars and galaxies. So what people have come up with, and what I'm currently working on, is this idea of primordial black holes. So these are black holes that are formed very early on in the universe. And one formation mechanism is from inflation again, so our old friend. And so these fluctuations that we see in the scene B, if you get them large enough, they can actually collapse. You can form large enough density perturbations that collapse and form primordial black holes. You do have to modify our sort of current standard picture of inflation to generate enough of them to be all of dark matter, but that is one possible way. And there are more sort of exotic methods, like the collisions of bubbles and like topological defects like cosmic strings collapsing in on themselves or colliding. And people are working on this, and it's sort of an active area of research. So yeah, at the moment, yeah, it's a definite possibility. And and I think it's something that we might have a better idea of in the next few years.
Awesome, thank you, Ashley. Okay, Ali Reader, when we look far away and only see the cosmic microwave background, we're both looking at the earliest moments of time and the edge of the expanding universe, right? If so, what % of the matter in the universe is part of this edge?
It's an interesting and maybe tough question. So the thing is, when we think of the edge of the universe, sometimes we might think that it is an actual edge, like there is a cut at some point, and that maybe matter could be distributed there. But what we have found so far with the observations is that if we zoom out from the universe, like if you're looking for very, very far away, everything seems to be very smooth, more or less homogeneous. And in a matter of fact, the percentage of actual matter contributing to the content of the universe is around 30%. And this matter is divided into two types. You have dark matter, which we've already heard some interesting answers about, and normal matter, which forms us, planets, and stars, and everything else. And dark matter even forms like, I would say 70% of the content of matter itself. So I hope this answered the question.
Okay, thank you. All right, I didn't have someone lined up for the next one. Does anyone want to jump in and answer the YouTube question? I have read a few things about the Great Attractor, and the galaxies seem to be drawn towards it. So is it a supermassive black hole? Can someone put their hand up if they want to tackle that one? I think, Rachel, maybe you wanted to, but yeah, I was wondering, you said you didn't have good internet, but okay, jump in.
I think I'm back. Yeah, I think I'm back. So the Great Attractor is probably a cluster of galaxies that is unfortunately in a part of the sky that we can't observe very well because our own galaxy is in the way. But so before the pandemic, I actually went to a conference in South Africa where folks were starting to find the Great Attractor because they're starting to make these observations, looking for galaxies, looking for clusters of galaxies, in a way using technology that kind of lets you peer through the galaxy. So that's both using radio frequency waves to look for neutral hydrogen, and then also using the infrared wavelengths to look for galaxies and to count galaxies. And so the Great Attractor has to be a lot bigger than a supermassive black hole. It has to be like hundreds to thousands and thousands of galaxies. So that's the kind of mass that we're thinking about. And so I don't think there's any observed supermassive black hole that could be that big, because supermassive black holes are sort of by design inside of a galaxy, which has much more mass. So hopefully that answered the question.
Cool, thank you. Okay, Daniela, do you want to answer why is there no center of the universe?
That is an interesting question. Because we checked, or rather, we did consistency checks. We can't make a direct check, but we can make checks that can tell us if it's not this way, and so far they all passed, or they didn't highlight any inconsistencies. This is part of what we call the Copernican Principle, and the scientific version of the Copernican principle, which is called the cosmological principle. Let me tell you a bit more about those. The Copernican principle essentially goes, we are not living in a special place in the universe. And of course, the problem with this is that this is metaphysics, this is not physics. How do you measure how special a place is? So then this is usually converted into the so-called cosmological principle that goes by all the places in the universe are equivalent and all the directions in the universe are equivalent. And the cool thing about those is that these are ideas that can be tested. So what do we know? We know that wherever we look around us, if we zoom out sufficiently, then the universe looks the same. This doesn't still prevent that we are at the center of the universe, though. It could be that maybe everything around us looks the same, but we are at the center. Well, all the consistency checks we have made so far tell us that this is not the case. And the mathematical model that we have and that works very well is one where all the places in the universe, provided we zoom out sufficiently, basically they're all, the same physics is happening in all of them. I should say that until we can generally travel to a different place, we can only make consistency checks, which means we can make these tests that tell us whether what we see is consistent with homogeneity rather than really putting it to the test. But if one day we can go and actually travel to a very far part of the universe and take astronomical observations there, then we could be able to make a direct test as well. Anyway, to answer your question, there could have been a center of the universe, but we checked and we didn't see one.
Awesome. Nice summary at the end. Well, not summary, but clear answer to the question. Cool. Next would be Angaran. What is the current thinking regarding any possible link between inflation and dark energy? And is there a satisfactory explanation as to why inflation stopped?
Okay. Yeah, so I think I kind of touched on this about the relation between inflation and dark energy. So if you want to look at it from a geometrical perspective, inflation and dark energy can be modeled by the same types of spacetimes that we call de Sitter spacetime in general relativity language. And in terms of was the last part? Sorry, Sean, what was the last part again?
Why did inflation end?
Why didn't? Oh, right. Okay. Yeah. So yeah, this is a very Okay, I could talk about this for ages. To answer it frankly, it might not have ended. We're not sure. There are various ways of thinking about this. So one potential way of thinking that leads to a concept known as the multiverse, and I think Hawking actually did some work on trying to avoid this problem, is that you have an eternal inflating universe. And what we mean by that is you have patches, what we call Hubble patches, as in the stuff that the universe that we see, but then you have various other patches which continue expanding, which lead to sort of like, well, yeah, multiverse. And then there are more, I guess, potentially sensible theories, like seem a bit more less like science fiction, which have come up actually again in this conference, trying to stop the inflating phase, which is caused by this quantum excitation of a field that we call the inflaton field, and the quantum excitation, in the same way that a photon is an excitation of the electromagnetic field, is the inflaton itself. And to get the inflaton to decay and give us a standard model of particles, we have these theories at the end of inflation called preheating and reheating. And there have been some very interesting discussions and talks on these in the conference, actually. And preheating and reheating are essentially saying we've got the inflationary phase in the early universe to resolve the problems of the standard classical hot Big Bang model, but then we need to go from that to the cosmic microwave background. So from the inflaton to the cosmic microwave background, which we know there we had standard model of particles. So we come up with theories to kind of stop the universe expanding and get rid of the inflaton by making it decay into what we get today, as in the standard protons, neutrons, electrons, etc. that we see. So yeah, you potentially could end inflation, or some people might argue that inflation continues forever. So yeah, there's so much I could say about that, but I will stop there.
Awesome, thank you. I think Ali Reader, you have a follow-up. Also, if someone wants to volunteer to answer Paul's comment after Ali Reader, or Ali Reader, if you want to answer it on your way through, then feel free.
Yeah, maybe I'll briefly talk about this, and if anyone else would like to jump in, that would be very nice. So I would just want to make a comment about inflation. It's a very successful theory. It explains a lot of stuff that we see today, but it's not the only theory there. We know that there are other theories, and one of them is called this cyclic universe. Now, I'm not sure if someone already asked this or if someone is going to ask this, but maybe it would be interesting to put it out there. And so we in cosmology always look at all possible explanations. We don't just stick to one of them. And when it comes to inflation, there are alternatives, and if people would be interested in hearing more about it, I can talk about it later on also. Concerning Paul's question, I will just briefly say that inflation per se doesn't require the universe to be finite or even infinite. And for sure, the size of the universe at the beginning was much denser than now, and that was one of the motivations, not motivations, but one of the consequences of inflation is to dilute the content of the universe in so very fast and a very short period of time, to explain the things that Ayran already mentioned. So if someone wants to jump in on that.
Okay, cool. Yes, Ashley, I think you had some thoughts.
Yeah, so it's mostly regarding sort of, why is inflation ended? And I don't think Angleton's some really good things, especially about eternal inflation. But one thing I think is worth mentioning is that if we take for a moment and assume that inflation did generate these perturbations we see in the C and B, then we can observe things like the spectral tilt, which tell us that during this period of inflation, that the expansion rate is actually lessening, and this suggests that. In some sense, that if you sort of carry that process onwards, you would expect it to sort of naturally end after a certain period of time, because the expansion rate is sort of slowing down in that sense. So if you sort of just, if you just take sort of the naive sort of observational picture of that, you would expect it to end from that point of view. Anyway, I just thought that was worth mentioning.
Thank you. Okay, Katie, did you want to mention one of the well-known alternatives to inflation?
Sure, yeah. So there are a few different alternatives that have been proposed for inflation, and my PhD advisor, Paul Steinhardt, was an originator of one of them called the Pyrotic Model, and that's one where there's a kind of contraction, a slow contraction of the universe that then results in a Big Bang, and there are certain reasons to prefer that model to the inflationary model, and I'm not going to take a position on that at the moment, but there are different ways of kind of trying to talk about the sort of pre-hot Big Bang phase of the universe, and what these models all have in common is trying to set up the initial conditions for what we observe as the hot Big Bang, this hot dense phase of the universe. And trying to use a previous phase of the universe to set up those initial conditions and to set up sort of what we understand to be the entropy of the universe at the early times. And there are all sorts of interesting questions you can get into about how natural or expected or fine-tuned it is to have these different pre-hot Big Bang phases, these different possibilities. So you can get into really interesting conversations about fine-tuning, about setting up these initial conditions, what it really leads to, whether you get the kind of universe that we see or not on all these models, and it's a very interesting debate at the moment in cosmology, what came before that hot Big Bang phase.
Yeah, just add my own kind of little thought on that. That those discussions quite often end up descending into discussions of what science is actually meant to be doing and what the actual philosophy of science is as what is natural, what is unnatural. How do we distinguish one model is correct when we maybe can't take more data? And I think that this is one of the issues we face in cosmology, is that it's an observational science rather than experimental science. And in experimental science, you can just keep taking more and more and more data to rule something in or out. In an observational science, you've just got the one universe to observe. And once you've observed it, that's it. You can't devise an experiment. You can get more and more and more clever at eking out tiny little pieces of subtle information from the universe, but it's still just the one universe. I think Aingaran wanted to have some comments about the ekpyrotic universe, so you can go next. And then we'll move on to something very, very observational.
Yeah, no, yeah, Katie made some very good points there regarding ekpyrosis. So, and I just want to kind of quickly jump in. So, one thing that we do in terms of quantum field theory in curved spacetime to do inflation is that we have this inflaton rolling down what we call potential, where it's like a potential well, and the mathematics from that allows us to get this slow roll. And what's interesting, and it kind of hints at the idea that I was talking about before about a duality between these theories, which one gives you a contracting universe and one gives you expanding universe, is that the pyrotic models use a fast rolling scalar field, or like we call it an inflaton if it's an inflating universe, but pyrosis just calls it a scalar field, and it is just a scalar field. And yeah, before maybe that question comes up on what a scalar field is. A scalar field is just a quantum mechanical field that we believe exists as theorists, and it helps a lot with getting the physics to look like what we see in the universe today. Because to quote Steinhardt, actually, in one of his talks when he was talking about these ekpyrosis models, was the universe is actually very boring. We started off initially back in the 50s, or whenever Fred Hoyle's steady state theory was the main concordance model. We started off with steady state universe, which said that the universe was symmetric in all aspects, not just all the spatial dimensions, but also in time as well. And slowly, with cosmology, we've realized it's a bit less boring. That's what led us to the hot Big Bang model. So it's no longer symmetric in time, but it's symmetric still in the spatial dimensions. And to get to that, you can do quite a lot of things, and that's why there's so many amazing theories out there to kind of explain it. But depending on how much, I guess, effort is put into developing these theories, those are the ones that then get the traction. And another thing I would point out, and maybe Steinhardt would hate me for saying this, is that he was actually one of the developers of slow roll inflation, and he's now moved on to these ekpyrosis models because he's got various physics arguments. It's interesting, just looking philosophically actually how science works in that respect.
Thank you, Aingaran. Okay, so we've been talking for a while about some pretty exciting, exotic theoretical stuff, but cosmology is a science, and the only reason that we can talk about this exciting theoretical stuff is that there are observers out there measuring stuff and telling us what the universe is actually like. So Rachel, our token observer in the panel, can answer the following question, which is not just a mundane observational question. It's a very specific question about probably the most important part of observation, which is removing all of the stuff you've observed that you weren't actually interested in. So yeah, Rachel, hello. What is the easiest strategy to avoid background microwave waves when observing the cosmos? There's so much man-made microwave pollution. How can the data not get contaminated, so to speak, when your instruments are highly sensitive? Thank you.
Yeah. So the answer is a lot of our technology uses the same wavelengths that we want to use as astronomers. And actually, the contamination from our technology is probably the biggest factor sometimes in where observatories are. So the ACT, the Atacama Cosmology Telescope, is actually located in the northern Atacama Desert, up extremely high at about 15,000 feet. And it's partially there because the water vapor is less in the atmosphere. This is a part. This is a part of the world where it rains very, very, very few times, but it's also up there because there are no people. So unfortunately, the way we deal with interference from people is actually go away from the people. And so actually my avatar image is a picture of me in the at Las Campanas, which is an observatory in the southern Atacamas in Chile. And it's about a 2-hour drive in a car from the nearest town to get there. So even in optical astronomy, we run away from people. It also means some of our biggest new facilities are happening in some of the most remote places on the planet. So a telescope that's being built now called the Square Kilometer Array is actually built partially in the desert, the Karoo Desert in South Africa, which is extremely desolate, and then partially in Australia, another place that has a pretty desolate desert. And actually one of the biggest costs for some of our facilities is getting the infrastructure, the power, and the internet to these facilities so that we can make the observations. Now, the coolest part is that there's actually a big radio telescope in West Virginia called Green Bank Observatory. And actually there's a person there. She's a very nice person, but is also very grumpy. And if you so happen to buy the wrong microwave or the wrong spark plugs in your, they will actually see it in their measurements to look for radio frequency interference. And she will show up at your door and say, no, 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 and take it away from you. So this is part of the radio quiet zone, which is a stretch in West Virginia. It's pretty quiet there to begin with, but there's some extra things there. So getting rid of interference from humans is one of our biggest issues, and it's why all over the world to put our instruments in really obscure places. Though West Virginia is not obscure. It's a lovely, lovely, lovely place.
Awesome, thank you. Okay, so we've just been joined by Deanna Hooper, who is a regular streamer on HAPS, so maybe a large proportion of our audience know her, but some proportion probably don't. So if you want to introduce yourself, Deanna, that's cool, and then we can give you a question to answer.
Sure. So my name is Deanna Hooper. I'm a postdoctoral researcher at the ULB over in Belgium. I'm currently actually in Germany because of the pandemic, but I'm technically in Belgium. And I work on dark matter, on the core questions of what if dark matter behaves differently to what we expect up till now, and what can we do to try to address this. And as Sean mentioned, I'm a regular here on HAPS. I have weekly live streams, so if you want to follow me here on HAPS, you'll get more cosmology. And on that note, just follow everybody here on screen in case anybody else starts streaming on HAPS as well. So yeah, I'm here on HAPS frequently.
Cool. Okay, and now you can answer a question. Let's see. Let's go with, is there any chance that dark matter and dark energy are just artifacts of us not getting the math right? That is, what's the chance that new equations for gravitation or expansion or something make dark energy just disappear?
Yeah, so I think that's a really interesting question. It's often phrased that dark matter and dark energy are essentially fudge factors to make our equations work. But the thing is, we haven't found anything that works any better. So some people are looking at this possibility that maybe dark matter is not the correct answer, maybe dark energy is not the correct answer. People are looking at modified gravity or ways of changing our existing theories. But nothing we've tried works as well as dark matter and dark energy does. So dark matter, dark energy are cornerstones of what we call the standard cosmological model, in which we have 25% of the universe in the form of dark matter, 70% in the form of dark energy, and only 5% with everything you see. And we have so many different observations, ranging from the tiny, tiny temperature differences in the background temperature everywhere in the universe, to the distribution of galaxies, the way stars move around galaxies. All of these things can best be described, with dark matter and dark energy. So sure, there is a chance that we might be wrong, but we've tested this. It's something we've checked. There's an XKCD for this, which has just been posted here in the comments as well, of maybe dark matter just doesn't work like that. It's like, yeah, believe me, we've tried. It's just still the best we've been able to come up with. Maybe one day we'll be proven wrong, but for now it is the best answer we have. So for now we're sticking with dark matter and dark energy.
I have some thoughts on this, so I'll jump in. I think dark matter and dark energy aren't necessarily on equal footing here. And I think dark matter is on a much higher footing, to the point that I'm happy to go completely on record as saying that dark matter is never going to go away. We're not going to be able to get rid of it. It's the same level of correctness as Newtonian physics. If something else turns out to be more correct, dark matter is a simplified, good model that explains almost everything that it needs to explain at the moment with one number, and it can explain stuff in the cosmic microwave background, how heavy galaxy clusters are, how fast they're moving, how fast galaxies are rotating. And I mean, those are just things off the top of my head. There's more. So it might be that the full picture is some sort of modification of gravity, but that modification of gravity looks like dark matter in a huge range of environments. And that dark matter model is so predictive. So yes, like Newtonian physics, got replaced by general relativity and quantum mechanics, but is still totally right where it's applicable and is taught in high school. So would be dark matter if it got replaced by some bigger thing. Dark energy, on the other hand, is kind of just, it is a little bit of a fudge factor. It's a constant vacuum energy that is causing the acceleration of the universe, but we don't really see it in as many diverse circumstances as we do dark matter. So because I was answering that, I haven't got a new question kind of already lined up, but we've got some things that people in our Google have been labeling as cute questions. So unless someone wants to follow up on that, maybe, is that what you
I was just going to help you out, Sean, and just say that we've got some questions I think maybe Rachel and Diana would want to tackle. So.
Awesome. Okay. Yeah. So let's see. Is dark matter thought to orbit around a galaxy along with the galaxy spinning? If so, why is it distributed spherically instead of in a more flattened disk? Okay, so let's make that the last question we answer. And I think that was for Rachel. And then we can go to these cute questions and then we'll wrap up because we want to be done in 90 minutes.
Okay, so the simple, well, it's not simple at all. It has to do with how different types of matter actually share energy. So the reason that a galaxy spins and forms a disk is actually because the stars are actually formed in the gas. And it's the gas, when it comes into the galaxy, that gets into the potential and can share energy, can dissipate energy, be collisional with each other, and actually form that disk. It's the same concept for why a solar system has planets spin around the central star. It has to do, it's a fundamental property of gas that I'm explaining very, very conceptually. Stars, however, and this is an analogy for how to think about dark matter, stars, however, are collision less particles. So stars never actually collide. They sense the gravity coming from everything around them and they move on smooth orbits. And those smooth orbits can be many, many different types of orbits opposed to what the gas tends to fall on in a galaxy. So the dark matter we also think is collisionist, and because of that, it can form a wide variety of different types of orbits, which we think are more spherical, or triaxial, which is really just like a squished kind of sphere. We don't know 100% exactly what this is called the halo of galaxies. We 100% sort of in observations because there's not much out there to measure. And it's something that my colleagues and I have been working on for a very long time. But we do have really good predictions from theory, and that's sort of the underlying physics of why we don't expect dark matter to be in a thin disk. It has properties that are different than the things that we see in the universe that do fill thin disks. And eventually, over time, as galaxies evolve, those thin disks get puffed up because our orbits work. And so actually, the stars eventually tend to be also in a spherical-like configuration, which isn't the most amazing answer because I fell back on science words instead of other words,
well,
but I'll work on it.
Okay, we're going to do a couple of cute questions, or things that have been labeled as cute questions, and then we will wrap up. So Ashley and Daniela, you haven't answered anything for a while. So do either of you want to tackle does dark energy or matter have a speed? My 4-year-old son was asking about the speed of light and if darkness has similar properties. Is that I see a smile from Daniela, so I'm going to just, do you want to have a tackle or not? Or we can try Ashley or... Yep, okay. That was a yes or?
Yeah, I think Katie also wants to add something. I was smiling. Okay, so the dark matter does have a speed. Okay, so if the dark matter is a particle, it does have a speed. Otherwise, you may want to... it's a bit difficult to answer, right? Katie, do you want to jump in?
Sure. So we think dark matter is probably made of particles, and those particles are moving around, sort of randomly in their clumps of matter. They're moving around throughout the universe, and so we do expect that they have a speed that's associated with them, in the sense that when they're inside galaxies, they have a certain kind of speed that on average, and when they're outside, they have a kind of speed. We do so if they are really, really fast, then that changes how much they can clump together. And if they're really slow, then it's easier for them to sort of fall into these clumps. So it's kind of like a heat, a kind of temperature we think of. So if dark matter is hot, that means that it's just moving around really quickly, and it's harder for it to get close together. It's harder for it to clump together. So actually understanding the speed at which dark matter particles are moving is an important question related to what dark matter is, because we think if it's a really small, really low mass particle, it can move a lot faster. And there are different kinds of ways that dark matter could form that could give it different kinds of speeds. And so if we knew how quickly the dark matter particles were moving, which we can get some ideas about by looking at how it clumps together in the universe, then we can learn something about its origin. We can learn something maybe about what kind of particle it is. I think there was a question as well about the speed of dark energy, and that's also a fun question. If we think dark energy is probably just something that's like a property of space, so it's just in space. It doesn't move around as far as we know, but it's sort of uniformly everywhere in the universe. So in that sense, it doesn't have a speed. But two parts of space can have a speed relative to each other, so you can think of it as it's just sort of bound to where space is.
Cool, thank you. Angaran, did you have something you wanted to add?
Yeah, to the person whose 4-year-old son was it? Do we know the name? But like to the kid, I feel like he would really like to know these cool names that we have for these dark matter candidates. So it came up in code word, Sean. So I had the difficulty of finding the word machos was apparently very difficult for us in our social events, and wimps. Those are the names that we give to the 2 categories of dark matter candidates. So machos are spelled MACHOS, and they stand for massively compact halo objects, and WIMPs stand for spelled WIMPS, stand for weakly interacting massive particles. Yeah, and I thought I missed a letter there, but I'm pretty sure you'll be able to remember those cool words, and be able to tell them around the school playground how you know about dark matter.
Cool, thank you. Okay, so we wanted to be done in 90 minutes, so we'll start wrapping up pretty quickly now. So Deanna wanted to answer this question. It's another one that's been labeled as a cute question, but I've read in interviews that many scientists were inspired to enter their respective fields because of an interest in sci-fi. Have any works of fiction motivated your research? If so, what were they and why?
Yeah, so I have a funny story to say to this, that I'm actually named after Deanna Troi from Star Trek. So my parents literally named me after a Star Trek character, and then they were not surprised I ended up being a scientist. But I think there was one piece of science fiction growing up that really had an impact on me, which was actually Stargate. It's just your standard sci-fi. Some stories are good, some are bad. But there's a character in that, Samantha Carter, who was the first female astrophysicist I saw on TV. Right? And she's a badass. She's one of the main characters. She's super smart, makes everyone else look stupid. And she's just this amazing, badass character. And it was one of the first times I saw a woman scientist on screen and being such a strong character. And it had a big impact on me of seeing this and thinking, this is the type of thing that I can also do. I mean, maybe not traveling through wormholes to go visit other planets, but it was a big inspiring figure for me. So I don't really want to talk about research inspired, but I just want to make a comment here about how important representation is, because it took me for seeing this astrophysicist on TV made me realize this is something I could do. So I just want to make the comment here that representation is extremely important.
Thanks, Deanna. Okay, so let's now look at wrapping up. So I think for a wrap-up question, let's go for, is there some aspect of your work that you think is particularly interesting but hasn't captured the public's imagination yet? Is there anything you'd like us to know that we might not think to ask? So on that topic, we will be actually doing recaps of the conference live stream. So whoever asked that, if you're on Reddit and are listening, keep coming back, because that's when we'll be sort of more talking about what we find interesting rather than just answering your questions. But does anyone in the panel want to tackle that question? Okay, so we'll start with Ali Rida and then we'll move from there.
So very briefly, I'm recently involved in studying quantum particles in gravity. And this is something that I find extremely fascinating. And I think that if we really ever find a signature for that, that would be very, very interesting for me. In particular, when it comes to neutrinos, which is something that I am much more interested in. If we were ever able to measure the effect of gravity on neutrinos directly, that would be something I would really like to see.
Okay, anyone else want to tackle that question? Okay, I see Katie's hand.
Yeah, so it's not something I work on specifically, but I think that I think people don't quite appreciate enough how amazing gravitational waves are, and the fact that we can detect them and what we can learn about the universe from them. And I know there's been there's been press about gravitational waves. It's gotten out there a bit, but I think that the fact that we can measure the vibration of space itself when black holes collide in other galaxies, like that's just so huge and amazing. And the way that we do the measurement being, the most precise measurement really ever done, and the technology that went into that, I just think like people need to know how incredible gravitational waves are. And I think that just, we can't talk about it enough, I think.
Yeah, totally agree with that. I guess underappreciated is a relative term, and even though gravitational waves are appreciated, they can still be underappreciated. So I think I agree with you on that. Okay, I don't think anyone else raised their hand when I was asking.
I've got something.
Okay, you reacted to the wrong comment in the private chat. Okay.
So yeah, no, I completely agree with Katie for one about gravitational waves, and I want to take this chance to actually answer a question I don't think we answered, which was about how far back gravitational waves can take us. And they can take us so far back. Like gravitational waves, as in the hint, they give us a probe of gravity. And in the early universe, with our current theories, we think that quantum gravity reigned supreme at the very beginning, because that's where we have these like mathematical anomalies, like singularities, the Big Bang singularity, that we only really understand using quantum gravity. In the same way that we don't really know how to understand a black hole properly without a full theory of quantum gravity. We need to use quantum gravity and understand the early universe, and gravitational waves give us that probe. And so being able to measure primordial gravitational waves, as in gravitational waves from the early universe, it's just, that is like a very exciting concept. And yeah, I think there was a massive announcement. I think it was back in, I can't remember when was the. Does anybody remember when the false
2014?
2014, yeah, false detection of gravitational waves. We thought we detected gravitational waves in the cosmic microwave background. Turned out to be dust. Really anticlimactic, but it caused a massive ruckus. Literally, academics were saying that they were going to be taking the week off or even longer if we had actually detected it. That's how big of a deal it was. And yeah. It was before we'd actually detected these astrophysical gravitational waves. Anyway, I'm diverting so badly. What I wanted to say was there's been a recent advancements which have been covered a bit in the public eye, but not too much, in terms of these new ways of approaching the early universe's understanding. So the way that we did it before was that we came up with models which were physically motivated by physical principles, but now we've come up with a way of using these physical principles to understand what we see observationally. So these physical principles I'm talking about, and they came up in one of the previous live streams, are locality, unitarity, and oh my god, why am I going blank now?
Causality.
Yeah, well, causality, we still need to, we still don't know how to really relate causality in de Sitter, but in de Sitter spacetime in the early universe. But yeah, it's these physical principles are like mind-blowing, as well as symmetries of the actual spacetime themselves to constrain these functions of that describe the observations that we see today. It's mind-blowing because before you would have this chain of physical principles model, then what you expect to see. Now we can just go straight from physical principles to the observations themselves. It's big. I can't explain to you how beautiful that is. And the people responsible for these advancements are in the Netherlands, such as Dr. Guy Helm-Pimentel, who will be, I think, on one of the upcoming live streams, and Professor Daniel Baumann, as well as some of my supervising collaborators in Cambridge. They've also been making massive steps in these fields, and I'm also excited to be working on it as well. So
okay, we're already over time, so I'm just going to go to Daniela for her answer to this question, which I think is also an underappreciated thing, and then we can wrap up.
Yeah, I think the cosmic microwave background is also underappreciated. Think about it. You're looking at the universe as it was 14 billion years ago. You're looking at the past, you're looking back in time. This is what things were like 14 billion years ago. Isn't that amazing? And in fact, think about what we see all around us now. Does it look anything like that? No, of course it doesn't, because everything was so similar, so homogeneous at the time that you could only differentiate things, only different up to one part in 100,000. Think about how similar things were. And I think it's quite amazing that we can look so far back in the past. If one day we can detect so-called cosmic neutrinos, we may go even further, but I'm not sure I will get to see that, maybe the next generation or the one after, but never say never.
Thank you, Daniela. I think my answer to that might be the polarization in the CMB, which I think hasn't captured the general public's imagination at all, but is one order of magnitude more impressive than the temperature of the CMB. In fact, my profile photo is of the polarization of the CMB. Ask me about it in another stream. So thank you everyone for coming. We will be doing this at least a couple of times next week, mostly us recapping what we've been enjoying about the conference and then answering questions that relate to that recap as they come. There will be one more general AMA answering questions of people on the stream and Reddit next week, probably on Thursday, but don't quote me on that just yet. And other than that, I want to thank all of the panelists for coming along and thank the audience for asking the questions on Reddit and asking the questions in the HAPS and YouTube live streams. Please follow all of our accounts. Deanna, as she said, streams weekly, so you should certainly follow her so that you can catch that weekly stream, but follow everyone else as well. And see you all sometime next week.